Welcome to Chapter 4, Organic Chemistry Problems. First thing we're going to do today is draw Lewis structures of the following free radicals. So the ethyl radical would look like this. The tert-butyl radical should be a carbon. Is a tertiary carbon radical. That's tertiary. This is primary. Isopropyl radical is the isopropyl structure with the radical on this carbon, and that carbon is connected to two carbons, so that would be a secondary. And the iodine atom, which would just be iodine with a radical. Okay, label each hydrogen in the following compound as primary, secondary, tertiary. Now, what I like to do is see the line drawing. So here we have 1, 2, 3, 1, 2, 3. And on this carbon we have a CH3 and a CH3. So we're talking about the hydrogens. So what you're not seeing here is the hydrogen. So if the carbon here is only connected to one other carbon, then it would be a primary. Those hydrogens would be a primary. The next carbon, since there's two lines there, two carbons, each one of those hydrogens would be secondary because that blue carbon here is connected to two carbons. The next one here, this carbon is connected to 1, 2, 3, so that hydrogen would be a tertiary. And then these methyl groups would be primary hydrogens, and this one would be a primary hydrogen. So primary, secondary, tertiary, and primary. Okay, let's go to the next one. We have this carbon connected to, let's do our line drawing. So that carbon connected to 3 CH3s, and that's connected to a CH2 and then a CH3. So let's do all our primaries. These would be our primary hydrogens. That would be primary. Those would be primary hydrogens. This would be primary, and these would be primary. The secondary then would be this blue one here. That would be secondary, and then there would be no hydrogen on this carbon here. Okay, going to the next one. Let's draw this carbon with two methyl groups, and then it's connected to this carbon here, and then this CH3 is connected to this one, so there's that. And then this is a CH2, CH3. Okay, so let's look at all our methyl. Our methyl groups are the ones I put in red. So each one of these hydrogens here would be primary. Then the secondary would be these hydrogens here in the blue, so these would be secondary. And then these black ones here, since that carbon is connected to three other carbons, this would be tertiary. This carbon is connected to three other carbons, that would be tertiary. Okay, these are a little bit nicer in the fact that these structures have already the line drawings. So these CH3 here would all be primary. Put those in red. And then the methylenes, which are just your CH2s, all have two carbons, so these would be all secondary. And then this carbon here is connected to three carbons, so that hydrogen would be a tertiary. Going to the next structure, the methyl group is right here. This would be CH3, so these hydrogens are connected to one carbon, they're all primary. Let's find our methylenes. These are the carbons that are connected to two carbons. These are the CH2s. Those are all secondary. And then the tertiary are the carbons connected to three carbons. So that would be a tertiary. And then as you see, the other carbon that we're not highlighting in that structure does not have any hydrogens. It's bonded to four carbons. Okay, going to this structure, we have primary hydrogens here, primary, primary, and primary. The methylenes then would be this CH2, this CH2, this CH2. And then our tertiary would be connected to three carbons. It would be this one here. That carbon to my right is connected to four carbons, so there's no hydrogen. 1, 2, 3, 4. That one's connected to four carbons. And then so this one would be also tertiary, and we also call that a methine. So you'll hear me call that a methine. A methine is just a carbon connected to just one hydrogen. If you hear me say methylene, let's see, how would you spell that? Methylene, that would be a CH2. So that carbon would be connected to two carbons. And then a methyl would be a CH3, and that carbon would be connected to one carbon. And so a lot of times I'll say these are my methylene hydrogens, my methine hydrogen, or my methyl hydrogen. Okay, so this question is asking us to rank the following radicals in decreasing order of stability. So the order of stability, these hydrogens here are the carbons, so the more substituted the carbon, the more stable the radical. So this means a primary hydrogen is going to be more stable than a secondary and the opposite. Erase that. Okay, so a tertiary hydrogen is going to be more stable than secondary hydrogens, which is more stable than methyl hydrogens. Okay, so methyl, which would be primary. So if you increase the number of carbons that are bound, then you increase your stability. Now the other thing you have to consider with stability is resonance. So this benzyl group here, so this is an aromatic or a benzene ring, and it's right next to the carbon. That is more stable. So that is probably, if not, I would say equally. So you just do equal as stable as a tertiary. And then you also have an allylic, which is, you'll see drawn like this, or you might see drawn like this. And so this is a carbon-carbon double bond right next to CH2. These carbon, this is sp2, sp2, and then this would be sp3. And these are just as stable as a tertiary. So when you do this, you classify them. So this would be a methyl, and that methyl, this would be a primary, because that carbon here is connected to another carbon. This would be a benzyl radical. This would be a tertiary. This would be a secondary, and then this would be an allylic radical. So I'm going to put decreasing order stability. So let's make number 1 most stable, and we're going to make the higher number the least stable. So benzyl would be number 1, allylic would be a number 1, and a tertiary would all be a number 1. So I would consider all three of these very, very stable. And then the second ranking would be number 2 is the secondary. Number 3 would be the ethyl radical, and then the methyl radical, number 4. So number 4 would be your least stable. Okay, for each alkane, draw the possible monochlorinated derivative. Circle the major product. Now, so this is monochlorinated. Which monobrominated derivative would be formed in good yield by free radical bromination? So let's just do the first problem first. Cyclopentane. It's not asking for a reaction mechanism, so we're just going to just do chlorine and H nu, and we're going to put, let's say it's monochlorinated. So that means you only get one chlorine per compound. Now, if you name this, no matter where you put the chlorine, you're going to get the same compound. So this is the only compound. Each one of these CH2s are equivalent. So we wouldn't be any different. Okay, methyl, cyclopentane, methyl cyclopentane. Now we have different hydrogens here. So we have a methyl here. We have a tertiary here, and we have a secondary here. So now we're going to get different products. So you can get your methyl, this Cl there. You can get the tertiary, and you can get the chlorinated here. And so now you also have to count. This is a 1, 2. So you can also get a chlorine here. So that would be a 1, 2, 3. So that would be a 1, 3. And if you get the chlorine here, that would still be a 1, 3. So those are the only products you can get for the monochlorinated chlorine. And it also says circle the major product. The major product is going to be the more substituted, because that's going to give you the more stable intermediate radical, that free radical here. That's going to be your more stable. The intermediate that leads to this product has a primary radical, and then the one that leads to these products gives you a secondary. So because this intermediate is the most stable, this would be your most stable product. Bromination would only give you one product, so let's just go ahead and do bromination. So of course this would be the same here. Bromination, because it's more selective, would only be this product. So you would not get anything else. Okay, let's do the next one. Okay, let's draw butane, and then 2, 3 dimethyl. Okay, so when you add your chlorine, you got to look at how many different hydrogens. So you got, I'm going to do the methyl, the primary ones in red. And so let's do those first. So if we got chlorine there, then we got to see if we named it differently. So this would be a 1, 2. So if we get it at this carbon, it wouldn't be any different. If we got it at that carbon, it wouldn't be any different, or that carbon. You can do that by naming them, because you go from left to right. The next carbon would be this tertiary carbon here. So what would that look like if you got a chlorination product on that carbon? It would be there. Now you think about the free radicals that lead to these, the intermediate free radical that would lead to this product. This would be a primary, and for this product it would be a tertiary. So obviously tertiary is more stable than a primary, so this would be the blue one that I circled would be your major product here. And then of course if you did bromination, that is the only product you would get, would be the bromine at the tertiary carbon. Okay, and then the last problem here is, see, tetramethyl butane. So we got two, here, let's keep it in the line drawing. So 2, 2, 3, 3 tetramethyl. All right, so let's do our chlorine and H nu, our light, and let's look at our primary. So we have each one of these are primary, and they only want the mono substituted product. So that would look like this. And you'll see that any of these would give you the same. And there's no hydrogen anywhere else, so this would be your only product, and that would be your most stable. And of course, if you get bromine, Br2H nu, your only product would be the bromine as well. And there you go. This problem asks you to write a mechanism for the light-initiated reaction of cyclohexane with chlorine to give chlorocyclohexane. So when you do a mechanism for a free radical, they only really need you to give the initiation step and the propagation step. So in the initiation step, you got to generate the free radical. So the light energy here generates the free radical, and you do want to show your movement of electrons. So in this bond, you have two electrons. One's going to go with that chlorine, the other one's going to go with this chlorine. Notice how I have my half fishhook arrows because they represent one electron apiece. And there's your two chlorine radicals. That's your initiation step. And this is called a homolytic cleavage, because lytic means you're splitting it. Homo means they each get the same. So they each get an electron. Now your propagation step. So we're going to do step 1. And if you recall from your notes, you've got to propagate. So the goal is for these reactions to add up to your overall reaction that you see here. And so you're going to have to get your product, and you're going to have to generate a free radical on the product side every time. And on the reactant side, you got to use up a free radical. So you always take the free radical that you got from your initiation step, and you react it with the starting material here. So in this case, it's cyclohexane. And then you're going to look at see which is your more stable free radical intermediate, which gives you the more substituted free radical. As you see, each one of these are CH2s, so they're all secondary hydrogens. So they're all equal. We call these methylenes. And so the chlorine radical will take off one of these hydrogens. The electron there is going to go there, and then the other electron goes to the carbon. So then your product looks like, and I'll just put these two electrons in there. Your product's going to look like, we'll actually make it red. See that electron goes to that hydrogen, and that electron goes to that hydrogen. So then you still have that hydrogen, and you have that free radical, homolytic cleavage, and then you get hydrogen with its electron forming a new bond with chlorine. And you can see that we generated one of the products here. We reacted with one of the starting materials, and now we've got to take this free radical intermediate. We call this an intermediate. It's our most stable free radical, and we've got to react that with, okay, that's our free radical. We got to react that with a neutral species to give us this product. So we can do that with reacting it with another molecule of chlorine. So you look in your reaction above, and as you can see, now this will go and attack. Now this is an electron, so it's negative. It's going to go towards the nucleus of the chlorine because the nucleus is positive. And then this one electron, homolytic cleavage, is going to go with the chlorine. That's going to form a new bond. And then this other one is going to go with that chlorine. And the purpose of your reaction arrows is to keep track of your electrons. And then you get the chlorine free radical. So that chlorine got that electron. Let's keep track. And those two electrons make that bond. And so, yes, we have our product. We've generated another free radical to continue on to propagate. We've got our HCl here. We have our fluorine here, and we have our cyclohexane. So if you add this all up, you'll see that the intermediates cancel out. So they're on both sides of the equation. The chlorine radicals cancel out as well, and you're left with cyclohexane plus chlorine. If you add these all up, your product here plus HCl. And that is how you do the reaction mechanism. Okay, bond dissociation enthalpies. Calculate the delta H for the following reactions. Now, when you do these, you got to keep track of the bonds being broken and the bonds that are formed. And then what you want to do, so you are going to keep your bonds broken, and bonds being broken will be positive values, positive delta H values. You will need to pull up this table. I pulled this out of your Moodle slides. It's in your book, and these are the bond association energies, and I'm going to have to look at those. And you need a calculator. So so the bond's broken. It always takes energy to break the bonds. To pull apart a bond, it's going to take energy in. So this is going to be an endothermic process. So we're going to have to make these delta H values here positive. And we're going to add all those up. And then we're going to keep track of the bonds formed. Now when bonds come together and formed, that's exothermic. It gives off energy. So we're going to make that delta H negative. So we're going to take those lists of those delta H values, and we're going to make those negative. And then we're going to add those up. So this should overall be negative, and this will overall be positive. And then you're going to add up all your delta H's for your total reaction. And so you're going to have a positive value for bonds broken. And then you're going to add your negative for your bonds formed. Negative. This should just be kilojoules per mole. This will be kilojoules per mole. And then you'll get an overall number, kilojoules per mole. And if it's negative, then that would be exothermic process. If it's positive, then it would be an endothermic. Okay, so let's do just that. So when you look at this, first, what bonds have to be broken? And you kind of think of, you can write the whole mechanism. So as you can see here, iodine has to break. Iodine's going to have to break, and so is this. You got to keep track of the classification of the hydrogen because it goes on a primary. So the primary CH bond has to break, and then the bonds being formed are this hydrogen here with the iodide, so HI, and then the carbon with the iodide. and it's going to be a primary. Because when you look at these, so if I go to Moodle, I'm going to make this really big so I can see it. I see the bond dissociation enthalpies, and then you can add them up. So I see iodide, and I'm just going to use kilojoules per mole, and I see that's 149. So this is 149, and while I'm here, I'm going to go ahead and get my HI, and that's 298. So I'm going to make that negative 298, and then I've got to go and find my primary CH bond. So you see the methyl bonds, and then you see primary. And so that's 423. We're going to make that positive because it broke. And then the CI is formed to our primary, and that's 238. So that'll be a negative 238. So when I get my calculator out, I'm going to do 149 plus 423, and I get a positive value of 572. And then I get, on my other side, negative 298 plus a negative 238. That gives me an overall negative 536. And when I put this in the equation, 572 plus a negative 536, I get an overall 36 kilojoules per mole, and that would be endothermic. Okay, so let's go to the next one. And I'm just going to keep the running total here. So bonds being broken have to be the iodide. So iodide would break. Oh, sorry. Let's do the next one. Okay, so we did this one. Okay, so HI gets broken because you see over here it's made HCl. So HI has to break, and this primary carbon chlorine has to break. So the chlorine is here, and the iodide is here. So those have to break. And then what has to form? Over here, we have CI. So the primary carbon iodide forms over here. And what else forms is the HCl. HCl has formed. So then when I go to my table, HI is 298 kilojoules per mole. The primary carbon Cl is 335, and then the bonds broken, the bonds formed are HCl, and you need to do this exercise so you can get good at this and get quick. So that's negative 432, and then we have a primary carbon iodide form, and that's 238, so we're going to make that negative 238. And then we add these together, so we get 298 plus 335. It gives us an overall 633 positive enthalpy. And then we have negative 432 plus a negative 238, so that's negative 670. So we do 633 plus a negative 670, and that gives us an overall delta H for this reaction, negative 37 kilojoules per mole, and that would be exothermic. Okay, let's go to the next one. The next reaction we have, we are breaking the OH bond here. So we're going to break that is, now we gotta look, that's a carbon, that is a tertiary carbon OH bond. So we're breaking that bond here, and we're going to make a tertiary carbon Cl bond, okay? And then we're going to have to break the HCl, and we are going to, we already make the Cl here, but then we're going to make a OH-H bond, a water bond. Okay, so now when I look, I'm looking for the tertiary carbon OH bond. I see the bonds to the tertiary, and I see an OH, and it's 401. So that's going to be positive 401 kilojoules per mole. To break that bond, HCl is 432. So that's 432. And then the exothermic of making the bonds, go back over here to my tertiary carbons, and I see a carbon Cl is 355. And that's negative. And then my water, H2O, is 497, so that would be negative. And so we have 401 plus 432. That gives us a positive 833 kilojoules per mole. Negative 355 plus a negative 497. We have a negative 852 kilojoules per mole. And so our overall delta H then would be 833 kilojoules per mole plus a negative 852 kilojoules per mole. And that equals negative 19 kilojoules per mole. That negative makes it an exothermic process. So that's an exothermic reaction. It gives off heat. Okay, so for our next one, I'm going to have to rewrite it down here. So let's just go ahead. Propane plus hydrogen. Propane plus hydrogen. And yields ethane plus methane. Yields ethane plus methane. Okay. So let's do this reaction. Bonds make, bonds break. That's backwards, isn't it? Yeah. Okay. So the bonds broken takes energy, and bonds made, exo, so negative. All right, so let's do this. Looking at this, we have broken this bond here. So this is a primary carbon-carbon bond. It's been broken. And we've also had to break the hydrogen. So we've also broken the hydrogen. What has been made is a primary carbon-hydrogen bond and another methyl CH3 hydrogen bond. So when we look at this, we're going to look at the primary carbon-carbon. So I'm going to my primary carbons, and I'm looking for a carbon-carbon. And I'm not seeing it. I see carbon-carbon bond. So here it is, yes, 377. Hopefully you can see the 377. That's going to be positive. Those are the carbon-carbon bonds. And then the hydrogen bonds are in the very beginning. It should be, let's look. Yes, it's the top one, 436. Okay, so the exothermic then, we're making a primary carbon-hydrogen bond, which is the top one of the primary carbons, which is 423. So that's negative 423 kilojoules per mole. And then we also have a methyl carbon-hydrogen, which is the top, and that's going to be a negative 439 kilojoules per mole. So we add these up, 377 plus 436. This gives us a positive 813 kilojoules per mole. And then the exo, negative 423 plus negative 439 gives us a negative 862. And so then when we add this up, we do delta H equals 813 kilojoules per mole plus a negative 862 kilojoules per mole. And we add that together with our calculator. We get negative 49 kilojoules per mole. and we call that an exothermic process because it's negative. And our last one, we have ethanol plus HBr. Go ahead and write that down. Ethanol plus HBr, and that gives us ethyl bromide and water. Ethyl bromide and water. Okay, so once again, bonds broken and bonds made. Bonds broken here. Obviously, this bond here is broken, which is a primary carbon OH. And the other one broken is this HBr. So HBr is broken. And then the ones made would be this one here, which is a primary carbon Br bond right there. And the other one made is this OHH. So H-OH bond. And so we look at our chart, and I'm going to find HBr first, which is 366. So that would be a positive 366 kilojoules per mole. My primary carbons with OH is 393, so that'd be a positive 393. And then I need a primary carbon with bromide, which is a negative 303 kilojoules per mole. And then we have water, which would be at the top, and it would be a 497, so it's negative 497 kilojoules. So let's add this up, 393 plus 366. That is 759 kilojoules per mole. And then we have 303 plus a negative 497. This is negative 800 kilojoules per mole. And now we do our addition. Our delta H equals 759 kilojoules per mole plus a negative 800 kilojoules per mole. And that equals a negative 41 kilojoules per mole. Okay, the next problem we have, the reaction diagram. So this is your reaction coordinate. Okay, you usually see like this, and then you have the energy, and it increases as it goes up. Okay, so we're supposed to label. So we're going to do the reactants as R, and the products. So usually the reactions is first, goes to the products here. So we call that reactants, and P for products. And then activation energy. Activation energy goes from the energy here to the very top. Okay, that's activation energy. So we'll call that AE1 for the first step. So this is AE1. And then the second step would actually be from this point here. This is AE2 for the second step. Now, I don't see, what does it say? Which points of the curve correspond to the intermediates? Okay, so I'm going to put an I here. This well down here, that's an intermediate. You will have to be able to label one of these for your quizzes and your exams. And which corresponds to transition state? So we're going to do transition state 1 and transition state 2. This is the highest point. So this is transition state 1, and this is transition state 2. It's the top of the mountain. Okay, those are your transition states. And is this overall reaction exothermic or endothermic? To determine exothermic or endothermic, it would actually be the delta H between these 2 points. Okay, so this is your delta H. Remember, it's your products minus your reactants. So this is where your energy is for your products, and this is your reactants. So it's this difference here that is your delta H. And since products, you can give imaginary numbers. So you can imagine if you want to make this 5, and then you go up here, and that's 10. Make it kilojoules per mole. So then you can look here, and you can see products is 5. Let's erase that right there. AE1. Okay, so if you did this with the numbers, so products, it would give 5 kilojoules per mole minus 10 kilojoules per mole. So that would be a negative 5 kilojoules per mole. So by giving it arbitrary numbers on this energy diagram, you can see that this is definitely exothermic, and the sign of the delta H here would be negative. Okay, label the transition state of the rate determining step. Okay, the rate determining step, RLS, the rate limiting step, rate limiting or rate determining step, is the highest point. It's the highest point. So it's your highest transition state. So in this case, it would be TS1. Does this structure resemble the reactants, the products, or the intermediates? So because of Hammond's postulate, so look that up in your book and read about it and write it down. It basically says that the transition state structure, so the organic structure of the transition state, resembles can be the intermediate, or it could be a product, or it can be a reactant that's the closest in energy to the transition transition state. So as you can see here, you look at the rate determining step right here, this point right here. This point right here is closer in energy to the intermediate. So the structure of the transition state, because we can't actually isolate that, transition state 1 would resemble the intermediate structure. Okay, draw a reaction diagram for a one-step exothermic reaction. Now keep in mind that was a two-step because you had an intermediate. So you had two transition states. So if we draw this, we're going to do reaction coordinate. That's your x-axis. And then energy increases. And it's a one-step, and it has to be exothermic. So that means we're just going to draw our products lower in energy than our reactants. So you can imagine if this was 5, if this was 10, 5 minus 10 would be negative 5 kilojoules per mole. So that would be an exothermic. So we label the reactants R, products P. Transition state here would be right up here, transition state. Activation energy then would be from this lowest point here to the highest point is activation energy, AE. And the heat of reaction, the delta heat of reaction then would be from the reactant to the product. So it's this energy here, delta H. And it's what we're actually subtracting here. So this is your delta H between the reactants and the products. In the presence of a small amount of bromine, the following light promoter reaction has been observed. Write a mechanism for this reaction. Explain why only one type of hydrogen has been replaced in preference to any other hydrogen in the starting material. So if you do your bond dissociation energies for the bromination reaction, you will find that it's very selective because the abstraction of the hydrogen is an endothermic process, and that endothermic process will actually make the transition state higher, and that transition state in the reaction diagram, according to Hammond's postulate, will make the transition state structure resemble that of the product. Okay, and so you want your most stable. Bromination is very selective. That's a key word here. And therefore, it will only make your most stable free radical intermediate. So in this case, you want to label your protons, you want to label your hydrogens, and you want to think about where your most stable intermediates are. Now, this is a mechanism, it asks for mechanisms, so we're going to have to do the initiation step and the propagation step. So the first thing you do for initiation is you have bromine and you have H nu, and basically these electrons get split to give us 2 bromine radicals here. Okay, so there's your 2 electrons. And then you want to do just your propagation step. Okay, so step 1, you got to go ahead and take that bromine radical that you just made, and then it's going to react with your starting material. So our starting material here is this compound right here. Now, you have a carbon-carbon double bond. So the most stable free radical will be the one that takes this hydrogen here at that carbon that is an sp3 carbon that's right next to your carbon-carbon double bond. And this will generate an allylic free radical. We'll make that in red. So these are our electrons here. And so this bromine will come here and react with that hydrogen. And then the electrons will split. One electron will go with the hydrogen, and one electron goes with the bromine. And to give you, the bromine, the carbon. And this is an allylic tertiary radical. Very stable. It's going to be your most stable. Okay, so let's go back to your propagation step. You took a free radical from your initiation step, you reacted with your neutral molecule, you produced a free radical, so you're propagating it, and you also have to produce something from the product here. Sometimes it's shown here, sometimes it's not, but that would be HBr. Okay, so you got to have a neutral. You see those are your 2 bonds being formed from the HBr. And then you're going to take this same intermediate here, your free radical intermediate, your allylic radical, and you're going to react with bromine again. That's your neutral. Here's your starting material. You want to propagate this, and this electron then will go and attack that bromine. The 2 electrons will split. One will go with the bromine, the other one will go with the other bromine, and that will be your homolytic cleavage. So now we want to draw our product here. These are our electrons, 1, 2, and we have now bromine attached, and we generated your bromine free radical here. And that's a neutral with the bromine. And as you can see, these are actually the same, I believe. Are they? Let's see. 1, 2, 3. No, they're not. 1, 2, 3. Okay, so the key here is resonance structure. And so when you have this free radical, you can just show this free radical here going through a resonance. So you got the electrons can move. So if this electron moves here and this electron moves there, it's a resonance structure, so they're equal. So then you want to redraw this, and you get this free radical. Okay? Now, so that's your resonance structure. Those are equal structures, hence the double-headed arrow. That means they're the same. So if they're the same in the resonance structure, then you could also write a third propagation step where you take this resonance structure and you react it with bromine. So let's do that, where we take our new resonance structure and we react that. So we're doing essentially that last step here, this step right here. We're going to react it with bromine. So this electron is going to go attack the bromine. The bromine is going to split homolytically, and then you get this product as well. You just redraw it. And here's your bromine. And then you generate the bromine radical. Now look at the structure and see how it's different from that structure, but it's also the same structure that is made here. So both are accounted for, and that's the answer. Okay, this is your last problem. For each compound, predict the major product of free radical bromination. Remember, free radical bromination is selective, so you're only going to generate the free radical that is the most stable. This is why you need to know your stability of your free radicals. And then that's going to brominate. So you're going to get a bromine on that free radical, stable free radical. Remember, the bromination is highly selective and only the most stable radical will be formed. Okay, so cyclohexane, and you react this with bromine and H nu. All of your carbon hydrogens are secondary, so you're just going to get one, and that's just the bromine. Okay, methyl cyclopentane. This looks like what we've done already. Methyl cyclopentane. So there's your bromine, H nu. You're going to get the tertiary bromination. Decalin. Decalin is a 10-membered ring. You can look it up, Google it. Decalin, you have the most substituted hydrogen would be this one. So since it's symmetric, you only have to do one. Oh. So that would be your bromine there. Hexane, 1, 2, 3, 4, 5, 6. What would you get here? The methylene. So you would get the bromine here, 1, 2, 3, 4, 5, 6. That's 2 bromo. You would also get 1, 2, 3 bromo hexane and 2 bromo hexane. 1, 2, 3, and either way you get, if it went from the other direction, the only thing you're going to get is 2 and 3. Okay. Ethylbenzene, this is going to generate your benzyl radical. So ethylbenzene would be this compound here, and you would generate the bromine there, the benzyl radical, and then F appears to have a allylic radical, so let's do F. And here's your bromine, H nu. So your benzyl radical would be here, or your allylic radical, sorry. Allylic radical would be there. And then let's draw your resonance structure. So let's draw that intermediate. If you took away that hydrogen and got your free radical right there, then your resonance structures, these are equal structures. The 2 electrons would, one would go there, and the other would go to this carbon here. So that would look like this compound here. And so if you take, remember these are equal structures, if you take this and then react it with bromine, you would get this product as well. And those would be your two products.